6, and it's called radicals. So if you don't remember what radicals look like, this is what the radical looks like. So we'll be dealing with all kinds of radicals. We'll be dealing with square root radicals, cube roots, and quartic roots, fifth roots or quintic roots, um, so on and so forth. And in general, we refer to these as nth roots. So we're just going to get down to the basics here. You do have homework for each lesson. You have 4 different lessons. You have a major quiz coming up here and a mid-chapter review, and then our Unit 6 test, which will be in January. So in the front, it's a big piece of blank paper, and I put a couple of things there, but my hope is that you fill this in as we move forward. Okay, and we're just going to get started. So lesson 1 is graphical characteristics of radical functions. So in general, the radical looks like that on a graph. Looks like this as a function. And the radical function contains a radical expression with the independent variable, usually x, in the radicand. And usually, radical equations, where the radical is a square root, is called a square root function. An example of a radical function would be y equals the square root of x. This is the parent square root function, and its graph looks like, well, we have to graph it. So we're going to do that. So what we're going to do is take the square root, and the graph looks like this. On the other hand, the graph of the cube roots looks like this. And we'll see that as we move forward. So the first thing that we want to do is just look at the graphical characteristics of y equals the square root of x. So the function family here is radicals. They are the radicals. Okay. And so one of the things we're going to want to do is to get our graphing calculators out. And while I'm waiting for that to pop up, I'm going to go ahead and fill in this table once I get my equation in. Okay, so I've got my graphing calculator to pop up here. I went to y equals. I'm going to press second, x squared, and type in the x. And there's my square root function. And I press second graph for the table. And if I look, there's no numbers, there's no y values for anything below 0. So I'm going to start my first point at 0, 0. My second point at 1, 1. Third is at 2, 1.41. The fourth is at 3, 1.732. 1.732. And we do different colors here. The square root of 4 is 2. Square root of 9 is 3. And the square root of 16 is 4. Okay? So I'm going to go ahead and graph these points. So first I'm going to graph 0, 0. It's right here, right? Then 1, 1 is right here. Then 2, 1.41. I'm going to skip over those decimals. Like these two, I'm just going to skip over these and focus on these right here if I can. So for 4, 2, so right 4 up 2, right 4 up 2. There's that point. The next point is 9, 3, so right 9 up 3. There's that point. And then 16, 4. So right 16 up 4, and there's that point. So now I'm going to carefully try to graph this this function, and she starts at 0. She starts at 0, and she keeps moving towards the right. So she's moving towards positive infinity. So for a domain, she starts at 0, this graph here, and she moves towards positive infinity. 0 is on the curve, so I put a hard square bracket there and a parentheses here. Now for your range, starts at 0, moves up, keeps going towards positive infinity. So from 0 to positive infinity. Is there an interval of decreasing, increasing? Yes, the interval of increasing is that domain that I have right there. It's the domain. So I'm just going to copy that. Right. And let's copy that domain here. So it increases from 0. So the y value always gets bigger to positive infinity. The interval of decrease is non-existent, so not available. X-intercepts is some easy stuff, guys. X-intercepts, where does it cross the x-axis? And looks like the x-intercept and the y-intercept are exactly the same. So I have 0, comma 0, and I always use parentheses for those types of things. So I'm just gonna type this because that wasn't working out too well for me. So parentheses 0, comma 0, and I'm gonna make that a little bit smaller. That's for the x-intercept. And then for the y-intercept, comma 0, comma 0, close parentheses, and there we go. And that means for my actual zeros, x equals 0. So the end behavior, as x moves towards the right, as it moves towards positive infinity, y increases. Y increases. Now, as x moves towards negative infinity, y goes to literally 0. It just stops at 0. Now, does x approach negative infinity? No. No, it does not. No, it does not. You cannot. The reason being, I want you to note it on the left-hand side. I'm going to note it as well. Okay, so for the square root function, x never approaches negative infinity because you cannot take the square root of a negative number and produce a real number. Okay, so the next part we're going to look at the cube root function. So we're going to change some things here. So for the cube roots, I'm just going to type these numbers in. You can use your graphing calculator if you need to. For the cube root, square root of -8 is -2. The square root of -2, I don't know that one, so we're going to go right here and do the cube root. So I go press math, number 4, and make sure I clear that out first. Math, number 4, and x. And I go to my table, second table, and I'm looking for what the y value is for -2, and it's -1.26. Negative 1.26. Okay, and for -1, it is -1. Just gonna change that here. Make that a little bit smaller there. So I have -1, 1, and 0, 0, 1, 1. And then here I have 1.25. I know because I just checked. And for 8, I have 2. So make that a little bit smaller there. There we go. A little bit haphazard, but it works. So just gonna go graph these numbers. So for -8, at -8, so left 8, down 2, and I make a point right about here-ish, right? -2, -1.26, so left 2, down 1.26, so right about here-ish. Let me make sure I did that right for this one. I need to go down one more, right down here. There we go. So much better. Now, and then -1, -1. So right about there, and then 0, 0, 1, 1, 2, 1.25, and then 8, 8, comma 2. So this looks like a half part of an infinity symbol. Look at that. Let's see if I can make that better. Because it's a curve and it looks something like this. There we go. So the great thing about the cube root function is it looks a lot like its inverse. So this function family is our cube root. It is the cube root. The domain is going to be from -infinity to all the way over to positive infinity. So I'm just going to draw those symbols. So -infinity to positive infinity. The range, same thing. Negative infinity, comma, positive infinity. Because the y values get bigger and bigger and smaller. Intervals will increase from the domain. It's pretty much you just repeat the domain. It's increasing from -infinity and all the way to positive infinity. That means, as a result, there's no intervals of decrease. Now x-intercepts, same thing here. It's going to be 0, comma 0, and y-intercept is going to be 0, comma 0, and as x goes to positive infinity, y values increase, so they go to positive infinity. As it goes towards the left, it goes to negative infinity. So it's a lot different than the square root function. For the square root function, you had no values on the left, but here you do, because you can take the cube root of a negative number and get a real number back. Next, we're going to transform radicals. So this is just a review of things that you already know how to do, guys. So just remember, if you add on the inside, you're moving left or right, add or subtract. Here you're moving up or down if you add a number on the outside or subtract a number. And if you multiply a big number, you vertically stretch. If you multiply a fraction, you vertically, you vertically shrink. So we're gonna graph these equations. The first one we're gonna do is the parent function. So we have value at 0, 0, 1 at 1, 1, 4, 2, and 9, 9, 3, 9, 3. Okay, and then just make your curve. And this is a parent function, so the domain is from Control Z. We're going all the way over to positive infinity. Okay, so I'm going to type the rest of this in here. And I have a hard bracket, and then 0, comma, and then we close that around a parentheses with a parentheses. On the bottom, hard bracket, 0, comma, and those y values go all the way up to positive infinity. On the other hand, for number 2, we're just moving everything up 5 units. We're moving up those key points 5 units. So I'm going to start with this point at 0, 0, and then my new starting point is going to be way up here. It's at 5. Okay? And then for 1, 1, my new y value is going to be 1, 6. So way up here. For 4, 4, 2, my new value is going to be 4. 2 plus 5 is 7. So 4, 7 right here. And then I'm just going to draw my graph. Draw my new graph. And it looks a little bit different because my range starts in a different place. So before, still going to positive infinity. Still going to positive infinity down here as well. However, for the domain, it still starts at 0. Starts at 0. Goes all the way over towards positive infinity. So for the domain, I'm going to type it in here. I have hard bracket, 0, comma, positive infinity, parentheses closed. For my range, on the other hand, starts at 5, goes over, I'm gonna just redo this. So starts at 5 and goes towards positive infinity. Alright, next one, I'm going to describe it first. I'm going to describe it in words. So there's a +2 inside, so it moves left 2, and then it moves down 1. You do it up here as well. Moves up 5. Each point moves up 5. So we use the same points, right? Same points. So for that 0, 0, I move left 2, and I move down 1. So I start at 2, negative 2, negative 1. Here's my first point. That means my other point, start at 1, 1, and move left 2, down 1. That's negative 1, negative 1. Let's make sure I did that right. Negative 1. So down 2, left 2, down 1. No, that's negative 1, 0. For 4, 2, I start here. I move left 2, down 1, or 2, 1. 2, 1. There's my new graph. So I'm going to create this graph. And my new starting point, my new domain starts at -2. It's at -2, and you make sure that you use that hard square bracket here. There's no parentheses, it's on the curve, comma, positive infinity. Your range starts at starts right here at -1, goes all the way up to positive infinity. So it starts at -1. This is referencing the range right here, and goes up to positive infinity. Now, number 4, you're going to do on your own. Please write out the transformations there. I'm going to do the cube root. Okay, so for the cube root, I'm just going to draw the parent function. I'm just going to do it in yellow. And we had a point at 0, 0. We had one at -1, 1, and 1, 1. And then 8, -2, and 8, +2. And my curve looks something like this. So that's the parent function. All right. Now I want to do this function where it moves left 1, excuse me. So I'm going to write out the transformations. It makes it easier. Each point moves left 1 unit, and then moves up 2 units. So at 0, 0, I move. This will be easier to do here. 0, 0, I move left 1, up 2, and here's my new critical point. For -1, -1, I move left 1 and up 2, and here's my new point. Okay, for -8, 2, I move left 1, up 2, and there's my new point there. And then, so I'm just going to go ahead and draw my curve going up. Okay, all right, so for my other part, I have this point, and it looks like it just moved up and to the left. So when I do my domain, it's the same as all cubic functions. It doesn't change. It's all real numbers, or -infinity, -infinity to positive infinity. Right? Range, same thing, -infinity to positive infinity. Hope your infinity symbols are not as ugly as mine. Next one, writing out the transformations. I have move left 1. Oh, guys, I did the last one wrong. It should be, let's make a correction here. Moves right 1 because it's subtract, moves right 1. So I'm going to be moving those points over. I'm just going to move the whole figure. Move right 1. Okay. And here's the other part. And there it is. That's actually more accurate. That is more accurate. Okay. So I'm going to take my parent function over here, and I'm going to move left 1, down 1. So left 1, down 1. So I'm just going to draw over it and move the object. So this is how a transformation actually works. Okay, so here's my object. Move left 1, and down 1. And there's my new curve. But what doesn't change is that the domain is still -infinity to positive infinity. and the range is still negative infinity to positive infinity. All right, so let's graph these. Just typical transformations here reflects over x-axis. Okay, moves left 2, moves up 3. Okay, so flips over, so moves up 2, left 3. Moves left 2, right up 3. So left 2, start at 0, 0, left 2, up 3, and let's see, 1, 2, 3. Okay. So there's my first initial point, and then I move down 1, and I keep moving over here, and here's my graph. Now the end behavior here, as x moves towards positive infinity, my y values are decreasing, so f of x goes towards negative infinity. My zeros here, my 0 is 7, x equals, let me just type that out for you, x equals 7. So if you graph it correctly, you can just easily see that type of thing. The next one, this function, only transformation I'm doing is moving right 2. Okay, so my new point is going to be at 2, 0. So I already know what my 0 is. It's at 2, 0. And I start at 1, 1. I move right. So that moves me over to 3, 1. And I can create my curve. And looks like y values on the end here as I move to the right are increasing towards positive infinity. My zeros here are x equals 2. X equals 2. There's my 0 right here where it crosses or hits the x-axis. For the cube root function, I would like you to do that for 9 and 10. Graph it. Tell me about the end behavior. You should get as x moves towards the right, you should get negative infinity. As x moves towards the negative infinity, you should get positive infinity. And the zeros here, I'm just gonna go ahead and graph it. So I move right 2, left 2, up 3. So left 2, up 1, 2, 3. All right, and graph a point. And my curve looks something like this. Looks something like that. All right. My 0 for this particular one, what the x value is when y equals 0, I'm going to use my graphing calculator. So I'm going to put this equation in and just look at it, make sure mine looks relatively close to that. So x plus 2. If you notice when I'm writing this in, I'm using parentheses, so plus 2, parentheses, plus 3. And it should have shifted, it should reflect over the x-axis. And because I need my negative in front, second insert, negative, and press trace. And looks close to my graph. Now, the zero, if my x values keep increasing, I have a 0 at 25. 25. When x equals 25, y equals 0. So graph number 10, do the end behavior and get the zeros. Now it says find the zeros of each function in your calculator or by graph. I'm going to do it in my calculator for number 11 and 12. So y, and I have clear the square root of 5x minus 7, get out of the radical, minus 3, and then I can press trace so I can look at it. I have a 0 right about there, so I'm going to press trace, see if I can trace the 0 here. So it doesn't allow me to do that. But what I can do is I can press second calc, go to number 2 for 0, I go to the left of that 0, press enter, and then I go to the right of that 0, press enter. And we want to round to any decimal places, so we got a 0 at 3.2. So if you put these in, the rule here to find zeros, you put the equation in to y equals, press second calc, you go to number 2, 0, and then create an interval around where it crosses the x-axis, and you should be able to narrow down your 0. So if you got lost, you need to play back the video so you can catch up. This is part 1 of this video. Please go ahead and get ready to check in for part 2.